Hello, dear students. Hopefully you are doing good. So, welcome back to a new video lecture. So, in the last lecture, we discussed about the predicate logic. We discussed about the prepositional function and the quantifiers. We discussed about the universal quantifier. We discussed about the existential quantifier, and we also discussed about the uniqueness quantifier. And then playing with those quantifiers, using the quantifiers, the prepositional function and the variables, we wrote the predicate, the different sentences, English sentences into the predicate logic in terms of the logic, right? And then we saw the different connectives with the with predicate logic, with these quantifiers and or negation and all these connectives we discussed with the quantifiers. So today we are going to discuss about the nested quantifiers, right? So like we discussed the in the previous propositional logic, the nested connectives. So here have a look. So these are this is a summary for today's lecture that we are going to discuss about the nested quantifiers, order of the quantifiers. We'll see how to translate from nested quantifiers into English language, and as well as mathematical statements into statements involving nested quantifiers. We'll see how we can translate English sentences into logical expressions, and at the end we see how we can use the negation with the nested quantifiers. So this is the summary for today's lecture. So let's start with the nested quantifier. What do we mean by the nested quantifier, right? So nested quantifiers are often necessary to express the meaning of sentences in English as well as important concept in computer science and mathematics. So nested mean we are having two quantifiers altogether. So here is an example. So we have, remember we have two quantifiers, that one is the for all, another one is the sorry, the other one is the there exists, right? So if we use both all together, for example, for all x there exists some y, right? And then p of x, whatever, x, y, whatever, right? So this is called the nested. So we have one quantifier variable with associated with the other one, right? In the scope of the other quantifier. So one quantifier in scope of the other quantifier. This may be like this. So for all x, for each x, there exists some x. For all y, for example, some predicate, right? So this for all y is in the vicinity of this existential quantifier, right? So it's in the scope of this one. So whenever this there is some predicate, some quantifier in the scope of another quantifier, we call it the nested quantifier, right? So nested quantifiers are necessary to express the meaning of sentences in English as well as important concept in computer science and mathematics. So we'll be looking for different examples today. So just to give you an example, so for example, every real number has an inverse, right? So how we can represent this with the help of the predicate logic with the statements. So so for example, you can see for all x there exists some y. What is the inverse? Inverse is when you add those numbers you get this zero mathematically, right? So for that, x plus y is equal to 0, where the domain of x and y are the real numbers. So x and y are real numbers, right? So they are real numbers, right? And then there is, for every x there is one y, at least there exists one y such that x plus y becomes 0. So this is how we represent using the nested quantifiers. We cannot represent this sort of a statement without the help of the nested quantifier, right? So you can also think about in another way. So we can also think of nested propositional functions. Like for example, I am talking about this one, there for all x there exists some y such that x plus y is equal to 0. It can also be viewed as for all x q of x, right? And this q of x is there exists some y, p of y, and this p of y is x plus y is equal to 0. So that means we actually can have the nested propositional function like we have seen in the previous class. So we have, say for example, let me, if I write it, so I have something p of x comma y that is equivalent to x plus y equal to 0, and for that I'm going to say there exists some y, right, such that p of x comma y is true, and for that this whole I am going to call it equivalent to the q of x, right? So so we can simply write it in terms of uh, p of there exists some x for all x q of x such that q of x is equivalent to there exists some y p of x comma y where p of x comma y is x plus y equal to 0. So that's how we represent it in the propositional function as well, but here we will try to write like this, right? In form of the nested quantifiers. For all x there exists some y such that x plus y is equal to 0. So when this becomes true, when this becomes false, that is another story. What is the truth value of this predicate function or predicate logic? That is another thing. So for example, for if x and y are the real numbers, and let me choose x as 5, right? Right? And I choose y any number. So for y, for x, there should be one y such that the answer becomes 0, right? So that is what, that is negative 5, right? So that's the inverse of this 5. So just to give you one example, right? Okay. So we can also think the nested quantification and the nested quantifiers in terms of the nested loops. So if you are aware with the programming, like I mentioned in the previous lecture as well, when we were talking about the propositional logic and propositional functions. So if you can think about the nested loops, right? So nested loops are something like, if I talk about the programming language, so for x, for example, starts with 0, right? X should be I mean less than or equal to 10, right? X plus plus, and inside this loop I have another loop in this boundary for j equal to, for example, or y equal to 0, right? Okay, y less than or equal to x, right? And y plus plus, and inside this I am doing some job. So this whole loop will be executing for every value of x. So if x is 0, this loop will be executed all the time. For the next iteration, when x will become 1, this whole loop will execute again for this for every value of x. This j loop will be executed all of the time, right? So the similar concept is here, the similar logic we are using here to see if for all x, for all y, p of x comma y is true. So I am going to check for all x, for all y, p of x comma y is true, loop through the values of x. So loop through the values of x, and at each step loop through the values of y. For every value of x, loop through all the values of y's, right, in the domain. So for example, the domain of x is 1, 2, 3, 4, 5, right? So x values are this one. So y values are, say for example, 1, 2, 3 up to 10, right? So if these are the y values, for every value of x, we have to loop through all the y values. For x is equal to 1, try this for all the y possibilities. For x is equal to 2, you have to check for all y values, right? So at each step, loop through the values of y. If for some pair of x and y, and for any pair x and y, if it is false, right, then for all x, for all y, p of x comma y is false, right? And both the outer and inner loop will terminate. If for any value this becomes false, for any pair x and y, it should be true because this is for all x, for all y. So this should be true for all x and for all y, because remember this, the quantifier says for all x, for all y's, right? So it means this should be true for all x and y values. So if it is true for any single pair, just the truth value of this will become false, right? And loop will terminate, right? So P of x, for all y, P of x comma y is true if the outer loop ends after stepping through each x. So if outer loop, this loop is ended normally, terminated normally for passing all the values of x and for all the values of y. That means, so there is no any pair for which x and y are false. So that means this is the quantification value is true, right? So now let's see one more example. See if for all x there exists some y. Now this is different. This is for all x, for all y. This is for all x there exists some y. P of x comma y is true, right? When loop through the values of x, you have to loop through the values of x. At each step, loop through the values of y, right? For all values of y, right? At okay, the inner loop ends when pair x and y found such that P of x is x and y is true. If a single pair is true, so the value is true. Why? Because it says for all x there exists y, at least one y for which this is true. So this will become true when at least one of the pair becomes true, right? So the inner loop ends when pair x and y is found such that P of x y is true. If no y is found such that P of x y is true, the outer loop terminates and this statement has been false, right? So if there is no such loop, such pair for which this is uh, true, so it becomes false, right? Clear? So in conclusion, for all x there exists y, P of xy is true if the outer loop ends after stepping through each value of x. So if it terminates normally, the outer loop x terminates normally for all the values of x, so it becomes true, otherwise it is false. So if the domain of variables are infinite, then obviously this process cannot actually be carried out. So this nested loop can only work here only when we have the domain values are finite. Domain is finite. So if the domain is infinite, so then the process cannot be carried out. This nested loop cannot work, right? So now let's look at the order of the quantification. So does the order matter or not? So what do we mean by the order? So which quantifier is first, or with what variable? For example, for all x there exists some y. For all, okay, so or we can say there exists some y for all x. So are they equivalent or not? So let's discuss in this order of the quantifiers. So let P x y be the statement x plus y is equal to y plus x, right? So if you can see, this is nothing but the commutative law of addition, right? Commutative law of addition of the real numbers. So assume that u is the real number, your universe or the domain is a real number. Then for all x, for all y, P of x comma y, and for all y, for all x have the same truth value. Yes, obviously. So if it is x plus y equal to y plus x, and doesn't matter, no problem. When we are saying for all x, for all y, P of uh, sorry, okay. So let me just rewrite it here. Okay, so for all x, for all y, P of x comma y is logically equivalent to for all y, for all x, P of x comma y, because this is a universally truth that the x plus y equal to y plus x, right? So this order does not matter. You write for all x for all y, or you write for all y for all x, right? So the order of the quantifier does not affect the result of the truth value. But let's say now in the second example, we have q of x comma y be the statement such that x plus y is equal to 0. Remember from the last slide, it's basically regarding the inverse. Assume that u is the real numbers, then for all x there exists some y, q of x comma y is true, but there exists some y for all x is false. So you can easily see that now here the values are different. This is not such any law. So I mean, in here, this is true for all x. There exists some y such that it becomes 0. X plus y becomes 0. But here there exists some y for all x. So the meaning is totally different. So what actually you are going to find here is, first of all, you are going to find for all x, right? Then you are going to say there exists some y. So there exists some y for all the x values. So that one y cannot be the inverse of, or for all other values, for all other x values. So this becomes the false, right? So order does matter in some, the order of the quantifier does matter in some statements, but in some statement it may not have any effect. So let's see a few questions on order of the quantifier. So let u be the real numbers, right? So u, the domain is the real number, and the defined p of x is x dot y is equal to x into y is equal to 0, right? So what is the truth value for each of the following? So whether is it true for all x for all y p of x comma y? So is it true or is it false? Yes. So what we are going to say, for all x, for all y, p of x is equal to true. So what should be the answer? It is obviously false. There does not have any x and y values. It's not always true for all the x values, and for all the y values it is not true. But yes, for some x values there exists some y such that this becomes true. That is the next one. So yes, what about this one? There exists some x, there are for all the x there exists some y such that p of x becomes true, means x into y is equal to 0. Yes, this is true. Why? Because you can see for all the x values, all the real numbers, there is one y, that is obviously 0 itself. If you put x and y, this will become 0. But here it is not true. For all other y values it is not true, right? That's why this is false, this is true. Next, for all okay, there exists some x for all y such that p of x is true. So what do you think? Is it true or false? There exists some x for all the y values such that p of x comma y is true. So right, so why? Because again, now here x has only one value. There exists some x, that is 0. For all the values of y, this will be true, right? Okay, so here for all x, there exists some x, there exists some y such that p of x y, whether it is true or false. Yes, it is also true. Why? Because for there is at least one x, there is at least one y, for that this becomes true. So order of the quantifiers are important when we talk about the mathematical and the logical expressions, right? Okay, one more example. So again, you are the domain is the real number, but x divided by y is equal to 1. That is a p of x, xy. So let's see. Well, now what happens? So for all x, for all y, p of x comma y. So what do you think? For all the x values means for all the real numbers, for all the y values means for all the real number y. So if you divide x and y, the answer is 1. Right? So obviously it is false. This is not true, right? Okay. Next, for all the x value, I mean for all the real numbers, there is some y value. There is some y value for all the x numbers, such that this becomes 1. X divided by y becomes 1. So what do you think? I don't think so. There is any number that can be divided x and y, and this will return in 1. Yes, x divided by x could be 1, y divided by y could be 1, but for x, there exists some y. I mean, that's false. Okay, now there exists some x for all y values, excuse me, p of x comma y. So what do you think about this? Right? So this is also false, right? So there exists some x for all the y. So I mean, that's again false. There exists some x, there exists some y such that this becomes true. What do you think? Yes. this is true for some x value, for a particular value, not for all the x values. For a particular y value, there exists some y value for some x value that becomes, so it becomes x divided by 1 becomes 1, right? So x divided by y becomes 1. So that's true. So this cannot be true for all the x, for all the y. This cannot be true for all the x with a particular y. This cannot be true for a particular x with all the y's. This could be true, this is true for a particular, for there exists some x, there exists some y, such that this becomes 1. X divided by y becomes 1, right? So quantification of the two variables, when it becomes true or when it becomes false. So in this table it is summarized. Say for example, if the scenario is for all x for all y, p of x comma y, or for all y for all x, p of x comma y, when it will be true. So it will be true, this is p of x is true for every pair of x comma y. So that means for all, for every pair. So it is false if it is not true for even a single pair. So then it becomes false. There is a pair xy for which p of xy is false. So this becomes false. This will only be true when it is true for all the pairs of x and y. Why we are talking about the p of for all x for all y, right? Clear? For all, right? So for all x, there exists some y, p of x comma y. When it will be true? It will be true for every x, all x, right? There is a y value for which p of x is true. So for all the x values in the domain, there is one y that is, for that this becomes true. And this will be false. When it will be false, there is an x such that p of x is false for every y. So this will become false when there is an x such that this becomes false for that value. For every value of y, this will be false. Another possibility, another statement, there exists some x for all y, p of x comma y, right? So when it will be true, there is an x for which p of x is true for every y. So there is an x, right? This is p of x is true for all the values of this y. Only then it will become true. Otherwise, for every x, there is a y for which p of x is false. If any single value of x it becomes false, this will be considered as false. For it should be true for all the values of x, then it is true. If it is false for any value of x, for all the values of y, this becomes false, right? So there exists some x, there exists some y, p of x comma y, or there exists some y, there exists some x for p of x comma y. So these two have the same order like this one, right? So this is true. This is a pair xy for which p of x comma y is true. So we are talking about the single pair x and y, one value of x, one value of y, for which this is true. This will be true, right? Similarly here, for one value of y, one value of x. So this will be false when this pair p of x is false for every pair x and y. For all the pairs, if it is false, this will be false, and otherwise it is, if it is true for a pair xy for which p of x comma y is true, this will become true, right? Now let's see how we can translate the nested quantifiers into English statements. Okay, so we have the statement for all x, right? We already have seen this statement in the last lecture. C of x is x has a computer, or there exists some y such that C of y means y has a computer, and f of x comma y, and we know that f of x comma y is x and y are friends. We have seen this in the last video lecture. So let's translate it into the English statement, English language. So that, what does that mean? That means for all x values, right? So C of x is x as a computer, f of x is x and y are the friends, and domain for both x and y consists of all students in your school. So now let's read one again. For all x, C of x, or there exists some y, C of y and f of x comma y, right? So if you see, for all the students in the school, either they have a computer or they have a friend y, they have a friend, that that has a computer, Y has a computer, right? So that's the solution. For every student in your school has a computer or has a friend who has a computer, right? So now let's translate this statement into English. So for all X, for all Y, for all Z, talking about all three values, f of x comma y, right, and f of x comma z, and x y is not equal to z. What does that mean? F of x comma y is x and y are friends. F of x comma z means x and z are friends. Y is not equal to z means y and z both are not same, right? So what does that mean? Or they are not friend actually. So they're not. So for all the students x, y, and z, right, means either they are friend, x and y are friend, x and z are friend, y and z are not equal, implies that y and z are not friend, right? So none of the friend is in common with x and y in this school. So there is a student, okay, there exists some x, sorry, I was talking about the for all x, there exists some x, so there is a student x, none of whose friend are also friends with each other, right? So none of whose friend is there is a student x, so y and z are not friend of that x, or they are not friend of each other, right? So some more examples, mathematical statements into the predicate logic. So for example, translate the sum of two positive integer is always positive in a logical expression. So how we can represent this is mathematical statement into the logical expression. So the statement is the sum of two positive integers is always a positive integer. So rewrite this statement to make the implied quantifiers and domain explicit. So let's rewrite it. For every two integers, if these integers are both positive, then sum of these integers is positive. So we rewritten this English statement into a way so that we can imply quantifiers on that, right? So now introduce the variable x and y and specify the domain to obtain. So for all positive integers x and y, x plus y is positive, and you can now easily write it in form of the logical expression. For all x, for all y, such that x is greater than 0 and connective y is greater than 0, if both is true, this is true and this is true, and this is the AND operator, this says this should be true, this should be true, that implies the sum of x plus y should also be greater than 0. So that's the implication. So for all x and y, um, if both are greater than 0, then the result is all the addition is also greater than 0. That means the for the positive integers, the sum of the positive integers is also a positive integer, right? Okay, let's have one more example. Use quantifiers to express this statement. There is a woman who has taken a flight on every airline in the world. So this is the statement, English statement. Let's convert it into the logical expression. So let's introduce some propositional function p of w comma f. B, the W has taken F, woman has taken the flight F, right? And Q of F comma A, B, F is a flight on that airline A, right? So the statement is there is a woman who has taken a flight on every airline in the world. So we have two propositional function, we have formulated it. One is P W comma F that says there exists some, the woman has taken the flight, and F of A, that flight is part of the airline, right? So now the domain of W is all women in the world. The domain of F is all the flights, and the domain of A is all the airlines, right? So all the flights, all the airlines, and all the women. Then the statement can be expressed very easily like, so there is a woman, so there exists some W, right? So W is the woman. So there exists some W for all the airlines, so right, who has taken the flights on every airline. So all the airlines, there exists some flight. So read it again, there exists some woman for all the airlines if there exists some flight. What does it mean? P of W comma, sorry, just wait, let me erase this. I don't know what. Okay. Okay. So for all this, P of W comma F means the woman has taken that flight. Q of F of A, that flight is available in that airline. And if this is also true, this is also true. So there is an AND operator, right? So there exists there exists a woman for all airlines. There exists a flight for such that P of W comma F and Q of F comma A. So this is the logical expression to represent this statement that there is a woman who has taken a flight on every airline in the world, right? So let's talk about some calculus in the logic. Let's take just to take an example. So use quantifiers to express the definition of the limit of limit of a real valued function f of x or of a real variables x at a point A in its domain. So if you recall the definition of the limit, so that is limit x is approaching to A, f of x is equal to L. So that's the mathematical definition of the limit. That is basically for every real number, epsilon greater than 0, right? There exists a real number sigma greater than 0, right? Such that f of x minus L is less than epsilon whenever x minus A is greater than 0 and less than sigma. This is the definition of the limit. So we can represent this with the help of the quantifiers. So we can say for all the epsilon, that's what we are saying there. Okay, for every real number epsilon greater than 0, for all the epsilon values, there exists some sigma, right, for all the x variables such that so 0 is less than x minus A less than sigma, and this implies f of x minus L less than the epsilon, right? Where the domain for the variables sigma, epsilon and the sigma consist of all positive real numbers, and the domain for x consists of all real numbers. So this is from the calculus for the definition of the limit function, right? So understand this, how we translated the mathematical function in terms of the logical expression. Some questions on the translation from English once again. Okay, choose the obvious predicate and express in predicate logic. Brothers are siblings. So what quantifier should we choose to represent brothers are siblings? Obviously, this is for all the brothers, for all the siblings, for all x and for all y. B of x comma y, brother of x comma y implies that siblings of x comma y, right? So brothers are the siblings x and y. If two x and y are two brothers, this is true. The x and y are true. X and y are basically the humans, all the boys in the world. So if b of x comma y is true, that means they are sibling. Siblinghood is symmetric. So see how we can represent this statement into the logical expression using quantifiers. So for all x, right, symmetric means for all x, for all y. If x and y are siblings, doesn't matter, y and x are also the siblings, right? So that means they are symmetric. So everybody loves somebody. So everybody loves somebody. So how we can represent? So everybody means there exists some x for all the x, there exists some y. Okay, everybody means for all, everyone loves someone, right? So x represent everyone, all, for all x there is some y such that L of x comma y, x and comma loves each other, right? Or x loves y. There is someone who is loved by everyone. So there exists someone who is loved by all, right? So there exists y, there exists someone y such that all x love x comma y, right? So there exists y, some y such that for all the x values, So I mean, we know that from the previous table when it will become true. There is someone who loves someone, right? So that means there exists some x, there exists some y, right? And L of x comma y. So there is someone who loves someone. So when we talk about single someone, so we talk about we use the existential quantifier. Everyone loves himself, right? So this is interesting. Everyone, it means for all, loves himself. So we have only one variable here, right? So for all x, right? L of x comma x. So that's how we are going to use the quantifiers for the English translation. Now let's see how we can negate the nested quantifiers, the negation of the nested quantifiers. So recall the logical expression developed 3 slides back, right? For there exists a woman who has traveled all the flights. So let's just go back and you can see from here, right? So there is a woman who has taken a flight on every airline in the world, right? So this is the logical expression that we have developed in that slides. So let's negate it. Using quantifiers to express this statement, there does not exist a woman who has taken a flight on every airline in the world. That is the negation of this one. So how we can negate this? So we apply the negation operator at the start of this whole statement, right? So that's the negation operator. That means the same. So now let's solve this using the De Morgan's law and De Morgan's theorem. So if you can say, here you can see, so how we can simplify this statement. So this is the negation of there exists some w, right? So if we apply the De Morgan's law here, so this existential quantifier will be converted into the universal quantifier, and we will move this existential quantifier next here. So for all x, now we have moved the negation quantifier here, and rest of the statement is same, right? So now in the next statement, we see now will apply the negation on this one for all a. So what will happen? So this for all will, the universal quantifier will be converted into the existential quantifier, and this negation will be moved next. So this is same, right? So this is converted, and now this is the remaining statement, right? Now let's see if we apply this negation to this quantifier, the existential quantifier, this will become universal quantifier, and negation will move forward. So it makes it universal quantifier and move the negation to the next, right? So rest is the same. So now if you can see, this negation is now with this statement, right? If we apply this negation to this statement, you know, this is the AND operator, this will be converted into OR, and the negation will be multiplied with both the propositional function. So that happens. So negation is multiplied with P of W comma F, negation is distributed to Q of F comma A, and this and is converted into the OR operator, right? So this is how we can, I mean, we solve the negation with the nested quantifiers. So if you want to negate a nested quantifier, nested quantified statement, you need to solve it like this way. So now let's translate the result back into English of this statement. So translate the result of this statement. How you will translate, right? So now you can see, for every woman, right? Now we have for every woman, there is an airline such that for all the flights, this woman has not taken that flight, or that flight is not on the airline. So if you will see, this and this actually means same, right? Okay, next. Return to the calculus and the logical example once again. So we for the limit, we establish this statement, right? We establish this statement without negation. Now if we apply the negation on this statement, similarly what will happen? If you apply the negation, this for all will be converted into the existential quantifier, and negation is moved forward, and this will convert this existential quantifier to the for all, right? And negation is move forward. And this for all will be converted into there existential, and negation is move forward. And here now negation will be distributed inside. So if you distribute the negation inside, here you can see this is one statement, right? This is another statement, and this statement implies this one. So we already know from the logic, Boolean logic laws that we studied earlier, that if there is a not P implies Q, this is logically equivalent to P and not Q, right? So we already saw this. So if we distribute this negation inside, what will happen? So this will be like this whole, right? And this implication will be converted into the AND operator, like you just put the values, and this will be negated. So when once we will negate this statement, so this is less than, this will be greater than or equal to, this will be converted into the greater than and equal to, right? So this one, so this is the resultant is logical statement, right? Okay, so therefore, to say that limit of x comma a function of x does not exist means that for all real numbers, limit of x comma a for f of x is not equal to L can be expressed as this Boolean expression or the logical expression or the statement, right? So that is for all L there exists some epsilon such that for all sigma there exists some x not of this one, right? And remember that epsilon and sigma range over all positive real numbers and x over all real numbers. So translating back into English, we have for every real number L, right? Now we are translating this back into English. For every real number L, there is a real number epsilon greater than 0, such that for every real number sigma greater than 0, there exists a real number x such that x minus a is greater than 0, and it is less, x minus a is less than sigma, and f of x minus L is greater than or equal to epsilon. So this is just to give you the idea that how we are using the negation with the nested quantifiers. Okay, some questions about the quantifiers. So can you switch the order of the quantifiers? Is this a valid equivalence? So is it a valid equivalence or not? For all x, for all y, p of x comma y. So for all y, for all y, for all x, p of x comma y. So is it logically equivalent? Is it true or is it false? Since we have seen in the previous slides, so when we talk about for all, so we can always see in the order that does not actually make any problem. So order does not matter here. Yes, the left and the right side will always have the same truth values. The order in which x and y are picked does not really matters. So let's talk about the next example. Next question, is this a valid equivalence? What is that? For all x there exists some y, p of x comma y. There exists some x for all, there exists some y for all x, p of x comma y. So what do you think? Is it logically equivalent? We have already seen in the previous examples when there are two different values, different quantifiers. So it is not really true to change the order of the quantifiers, right? So no, the left and the right side may have different truth values. You can prove it using the truth table as well. For some prepositional function, for p, try x plus y equal to 0. For p of x with u being the integers, so the order in which the values of x and y are picked does matter here in this particular statement. Now let's see the third one about the distribute. Can we distribute the quantifiers over logical connectives? For all x, p of x and q of x, is it logically equivalent to for all x, p of x and for all x, q of x? I mean, for all x, we are actually distributing it among the insides, right? So is it true? Yes, this is true. The left hand side and the right hand side will yield the same results, right? So this is logically true. So you can always, if there is only one quantifier, you can always convert, I mean, you can distribute it and you will, this is logically equivalent. So now let's talk about this one. How about the, okay, if this is OR operator, even then you can do that. So you can do with the AND operator and or operator, right? So what about the implication? So is it true for all x p of x implies q of x? So can we write for all x p of x implies for all x q of x? Obviously not. We cannot do that, right? The reason is very simple, because this will yield one result, right? This will yield another result. So here we are talking about for all x p of x, for all x q of x. Here we are talking about for all x p of x implies q of x, right? So no, the left and right hand side may have different truth values. Pick x is a, for just to give you an example, x is a fish, and for p of x, x has scales, right? For q of x, with the domain of discourse being all the animals, then the left side is false, because there are some fish that do not have scales, right? But the right side is for true, since not all animals are fish. So both have the different values, so this cannot be equal. So this is not logically equal, right? So for this is all for this lecture. So what we discussed in this lecture, just to give you just to revise it, just to give you the conclusion, we discussed about the nested quantifiers. We discussed about the translation of English sentences into the statement and statements into the English sentences using the nested quantifiers. We talked about the negation of the quantifiers, right? So prepare your questions. We'll come back with the new topic with the new lecture soon. Take care. Goodbye.